Hello everyone. Why every one of you present last class? I think maybe one or two. Hopefully you already got the video in the classroom, right? So you didn't. I think both of the videos and slides will be uploaded today or tomorrow. Okay, so they are ready. So the slides are actually basically the same like the previous class because I couldn't finish the previous one. Both the slide will be just like same file, okay? And the video will be also uploaded today for both the classes, like today and the last class. So as you remember, like last class, we discussed how we can actually implement a Boolean function. If I give you a function, you can actually uh, take several gates and implement that particular function, if you remember. So, for example, here, as you can see, this is a Boolean function, right? So, if I just ask you to uh, draw a or create a uh, circuit that implements this, how will you do it? So, you are already familiar with Boolean expressions, right? So what does dot means? So dot means and, right? If I say A dot B, that basically means A and B, right? And if so C dot D basically means C and D. So let's implement these two first. So we have A, we have B. If we AND these two input, we get what? A and B, right? Similarly, if we just implement C and D, we get something like this. C and D. And this is A, B. So this is basically C and D. And how we actually make a OR between these two. You see? So if there is a plus, that means it is OR. So if we just take a OR of these two, one sec. So OR is basically something like this. This is OR. But we have a bar function over, which is basically means it's a NOR. So if we NOR this, then we get what? This full function, we get an F. So this is actually how we implement a Boolean function in gate level. So let me ask you, how many transistors are in there? If I actually discussed last class, right? So we have 6 transistors here. This is not uh, a NAND gate. This is AND gate, and AND gate has 6 transistors. This is as well. This is also 6 transistors, right? And this is a NOR gate, which have 4 transistors. So how many transistors do we have here? 6 plus 4, which is 16 transistors in total, right? 16 transistors. So let me actually tell you, we can actually implement this particular function, this particular Boolean function in with lower number of transistors. So today's class, I will actually discuss how we can implement a Boolean function without implementing the individual gates. We can directly implement the Boolean function itself. So for example, I have instructed you to implement this whole function, right? Like A plus B plus C plus A and B or C and D and basically a bar. So let's say if we have two input, let's say X and Y, and if we just do this, it is X or Y. But if we do this, it's X nor Y. You see? So when we give a bar, it means we are implementing a NOT gate. So this bar means basically NOT gate or inverter. So basically that means is a OR function, a OR function or a OR gate, and then we have a NOT gate in front of it. What does it make? It's NOR gate, right? It's basically NOR gate. So actually what I am trying to give you here is we don't have to actually implement individual gates to implement a full Boolean function. We can, by the way, we can do that. This is correct. This is 100% correct. But if we want to implement it with lower number of transistors, we have the choice to do so. Now, in this class, I will actually try to discuss how we can do it. So for doing this, always look at the functions. Okay. For example, here we have a function like A and B, C and D, right? Let me actually go over the board. I think that
Yes. Yeah, you go ahead. Thank you.
so we have the uh, objective to implement this sum. So you already know how to implement it in different gates, and non, NAND, NOR, and OR, something like that. But let's actually try to do it in a different way. Actually, let me give you the steps to do it first. Then I will explain how that works. So for example, always look at the smaller sections of the Boolean function, smaller part. So think about it. We have A and B, C and D. And if you remember, like, what does AND means? AND turns on or AND gives away one and both are one, right? And think about NMOS. NMOS turns on when this is one, right? So if we have two NMOS like this, if we have two NMOS and we have A, B, then these paths will be on when both A and B are one, right? Think about it. So do it first. A and B. So we have two NMOS. They are in series. A and B. This is not AND, by the way. I'm just giving you an idea how to follow the steps. So take two NMOS. If there is a dot or AND operation, connect them in series. Okay. Then make C and D. How will you do it? C, D. Okay. Can you follow? We make smaller portions of it. Okay. If we have a dot or AND, then we just connect to NMOS like this. Now, we had C and D, which connect to NMOS like this. Now, how are these two connected? They are or with each other. So make them parallel to each other. Am I clear? So if we have dot, we connect NMOS in series. If we have or plus sign, connect NMOS in parallel. Okay. Then after creating the smaller part, connect them together. Okay. So let's connect them together. Then last class I discussed, it is a pull down network, right? We have two different networks, which is like pull up network and pull down network like this. So pull down network has what? NMOS. And pull up network has what? PMOS. So we are done with our pull down network. This is our pull down network. So when we implement it in NMOS, when we are done, our pull down network is done and give a ground here. Now we will design our pull up network. Do exact the opposite. What you have done for the PMOS. Look at here. You don't have to look at the function again. Look at here and do exact opposite for the pull up network. So what do you have here? Two NMOS in series. So we will have two PMOS in parallel to make them. So make two, instead of two NMOS in series, now we will have two NMOS in parallel. A, B. Okay? No, we have two NMOS in series. The equivalent pull-up network will be two PMOS in parallel. For here as well, we have two NMOS in series. For here, we'll have a two PMOS in parallel. So let's make it again. Like two PMOS in parallel. Make it somewhere first. We don't have to actually Now, these two branches are in what? Parallel, right? This whole thing and this whole thing are in parallel. So here, this whole thing and this whole thing will be in series. Are you guys following me? So here, these two whole thing, A, B, C, D, are in what? Parallel. Now make these two, I have made these two, right? Make these two in series. How can I do that? We can connect one after another, right? So it will be something like, just shift the whole thing here. C, D. This is our pull down network. So we have pull up network, design it first. Pull down network, and then do the exact opposite of pull up network. Then we are done. However, there is a catch. I will discuss it here. And this is our output. Our output will come from the connection where the pulled up network and the pull down network come from. And above the pulled up network, we have VDD or high voltage, and pull down network, we have ground. Okay. So please let me know if you have any question. I will go through a few of other examples. Don't worry at all. But think about it and let me know if actually this makes perfect sense or not for now. Are you guys lost or something? Okay. So the thing is, like, we have for implementing any Boolean function. So our target is to implement this Boolean function. Okay, this Boolean function. So let's so for the new car, so you don't have to think about it. How does it work? Follow the steps for now. You will eventually figure out how this works. So you have two network. One is pull up network, which will actually take the output to VDD. And you will have a pull down network, which takes the output to ground. And input will go to both of them. So you see input A has gone here and gone here as well. Input B has gone here and gone here as well. Input T, same goes to input T. All the inputs will go to the pull up network and pull down network, both, right? And the task of the pull up network is to take the output to where? VDD. For particular logics, when the output should be 1, the pull up network will somehow take it to VDD. And what is VDD? Once. Basically, high voltage means once. And when the output should be 0, somehow the output will be connected to ground and the output will be 0. Logic will be 0. And here our characteristic given there. If we have a Boolean functions, I don't know if you know what Boolean function is. So Boolean function is basically if we express something, the logic in a function. So for example, if I say 1 plus 2, we are say mathematics, right? Add two numbers which are 1 and 2. So we have Boolean expressions like this as well, like the gates. Do you know AND gate, NAND gate, NOR gate? So we are expressing this in equation, not equation, sorry, an expression. So it is called A and B. This is called AND, C and D. And there is a plus. Plus means OR. So dot means and plus means OR. So how we do it? Let's go over it again very briefly. At first, look at it. If there is a dot between two input, make two NMOS in series. If there is a dot in these two inputs, CD, make two NMOS in series. Now, these two, A, B, C, D, there is a what? A OR between them. If there is a OR, make them two parallel. So, dot means two NMOS, dot means series, and plus means parallel. For the NMOS, by the way, don't design the PMOS. I'm saying only design the, it is for the NMOS. Now, do exactly opposite for the PMOS. Exactly opposite. Two NMOS in series, two PMOS in parallel. Another two NMOS in series, two PMOS in parallel. They are in parallel. These two is in 6. Exactly. Then you will have your logics. However, there is a issue. Issue means we have implemented our design here, right? And did the exact opposite here. What is this doing? Taking the output to where? Ground. That's why whatever function we have implemented, A, B, C, D, we actually implemented the opposite. We have actually implemented A and B, C and D, or between them, and there is a bar. We are actually implementing opposite. Why? We have implemented it in NMOS, and NMOS taking the output to where? Ground. If the NMOS would, let's say in a hypothetical world, if take it to the VDD, then we actually implemented this. But we did not. We have actually implemented what? This. So if we want to implement this, just connect an inverter, not get. You already know how an NOT gate works. Then we have actually implemented this. Are you guys following so far? Please let me know if. So let's actually try a very simple function. Okay, first. More simpler function. For example, let's try this one. Okay, give it a try. We'll practice it a lot so that you will try to get it done. Give it a try. So think about it. How many inputs do we have? 3 inputs. Okay. So again, for the dot, connect the NMOS in series first. And for the, we have parallel. Okay. NMOS. And then, and at first, make the smaller parts first and then connect them. So I will just give you just 2 more minutes. Don't worry if you don't get to the point. Well, I will explain it. Okay. So let me actually ask you first. Okay. What are the small parts? Don't have to go to the big function first. Okay. What are the small parts? 2 parts. That one is this, another one is this. Right? 2 parts. First, implement this. And plus sign means or. How do we implement it? Parallel. So 2 NMOS in parallel. Do it. 2 NMOS in parallel. And one is A. One input will go to A. Another G will be B. Then there is C, just in MOS, just a transistor. So this will look like something C, okay? Now, we have implemented A plus B and C. And how are they connected? There is a dot. And dot means what? Series. So just connect this and this in 6. Now it's down. You pull down, network is down. Are you guys with me? So if you have a pull down network, don't look at the function anymore. Just look at it and do the opposite. For what? Pull up network. So how do we do the opposite for the pull up network, correct? That is the question. So write it here. How do we actually make the pull up network here? So we had A and B is in what? Parallel here. We make AB in series. Okay. A and B, sorry, it is PMOS, right? PMOS. They are series. And we have C, right? So another PMOS, let's say here. And these two parts are in what? Series here. They will be parallel. Done. This will go to VDD and this will go to output. This is our, by the way, so far you're okay? So whatever we have done here, A and B in parallel, you see A, B series. C is in series with this, C is in parallel with this, the whole two, okay? Now we have an output which is A plus B dot C bar. How do we remove this? By connecting a NOT gate. Then we have here we have okay. So if I initially ask you to not implement this, then you would not need this one. Now since I ask you to make this, you need an inverter bank. Okay. So here, whatever you have implemented actually, it is the complement. Because NMOS actually takes the output to wire 0. But I am trying to design a function which should be 1, right? When I give 1, 1, 1, what happens? 1 or 1, 1, what happens? 1, 1, 1. In Boolean, right? But the MOS will take it to where? 0. So this is not actually this function. This is actually this function. The complement of it. Now, how do I make this connect a NOT gate? So if you connect a NOT gate to minus, so if you flip a bit twice, it comes back to the bit again, right? So that's what is happening, NOT and NOT. So you are actually connecting a NOT gate here. And then here you are getting A plus B dot C. See, A plus B dot C. You guys are with me so far? Yeah. Bar. Yes. Now when I connected the inverter, we are getting A plus B dot C. There is a way, but I am not gonna discuss because it's gonna mess up. So think about it. We have implemented in MOS. We have to simplify the Boolean function in such a way that we can implement it in PMOS. So PMOS takes it to 1. Then we have to do very different. So I will not go to the details. Yes, there is obviously a way. That's a very good question. So let me actually ask you, how many transistors do we have? 3, 6. And NOT gate, how many transistors NOT gate have? 2. Right? So 3, 3, 6, 6 plus 2 what? How many? 8 transistors. Now, if Yesterday, I asked you, okay, implement this function. You would not do this. You did something else. You did something like this. A or B. Then there is a C. Then you make what? An AND gate. Right? This is what you would do yesterday. If I ask you how many transistors here? Here it is 6 transistors. How many transistors now? 12 transistors. Have we achieved lower transistor or no? No. NAND and NOR as 4. Yes, because if you follow up the last class, whoever had come new today, if you don't follow this number of transistors, go back to the previous class slides. You would see the slide. There is schematic diagram where I have shown how the schematic looks like. How many transistors are in there? NAND and NOR has 4 transistors, and NOR has what? 6. So 12 transistors. How many transistors do we have? 8 only, right? 6, 2. So, yeah, but no, inverter is for the just to achieve this opposite area. But think about it. If we have a much complex Boolean function, much complex, we will have much lower number of transistor counts, right? Let's go back to the previous function that I tried to implement, right? A little bit of I hope you have taken. So if you try to implement it, how many transistors we had before I erased the board actually? We had 10 transistors only 10. But if we implemented gate like A and B, C and D, then doing a OR, we had 18 transistors. But if you had taken the note for the first circuit I provided, we had only how many? 10 transistors. Now 18 to 10, you see? For more complex EI functions, we will see much more difference. If we implement the function directly without going to the specific gates. That's what my intention is. You can directly build a complex function. You don't need to build individual gates like this. Then you will have higher number of transistors. Definitely, because each transistor are having their own area, right? Consuming own area. So, for example, here we have 18 transistors, but if we implement it directly, we have 10. Almost half the number of transistors. 50% area is huge. So that's that's why this is used for. Let's try to build a little bit more complex function because it will be really. For example, do you know how computer does addition? We have here addition, like each add bit by bit. Have you ever taken any course where you had added binary numbers? For example, if I ask you, add 10 with 8. Okay, 80. Computer doesn't do it, then it's right. How many of you are familiar with binary numbers? So what is 10? 10 is basically, this is 10. What is 8? Yeah. This is 8. So what binary does is binary actually take bit by bit. Oh, wait on. I think I'm wrong. So this is basically what? 80. So what binary does is, like, what actually computer does is, computer actually adds bit by bit. So for adding each bit, we have adder. And what is an adder? Do you know? Adder is basically a Boolean function implemented by transistors, right? So, for example, in an adder, we have to implement somehow. Let me actually show you. So if I tell you What is 1 plus 1? 2. I'm talking about binary. No, binary is not 1. 1 plus 1 is 2 in decimal. Binary is 1, 0. This is called sum. The first one from the right side, and this is called carry out. So we are adding 1 bit with 1 bit and getting 2 bit, right? Yeah, if we add 1, 0, we'll get 1 bit. But we can specify 0, 1, right? If we add 0 and 1, we will get 0, 1. So we have 2 bit. Basically, if we add 1 bit, we are getting how many bits? 2 bits. The rightmost one is called sum, and the leftmost one is called carry out, which is sent to the next bit you want to add. So do you know how what carry out looks like? If we have 2 binary bit A and B, do you know what carry out looks like? Carry out is and by the way, we had carry in from the previous bit, right? We are adding 2 number, let's say. So we have 1 and 1, 0, and the carry out will go to the next bit, right? So we are adding 2 bit and we have a carry in. We have a carry in. Do you know what the carry out looks like? It's look like this: A and B, or B and C in, or C in and A. This is carry out. Now, if I told you to implement it in gates, now you know why we need transistor. Why I did the last discussion. So if I tell you, okay, implement this. So okay, you will go ahead and do this. A, B, 3 NAND gate, AND gate, something like that. B, C in A, and do what? A OR. You would do that, but now you will not do it because you know it has more transistors, right? So think about it. I am talking about adding 1 bit with 1 bit. This is the number of transistors you are actually, wasting, right? So we had 6 transistors, 6 transistors, 6 transistors. And do you know how many transistors we have here? Is also much higher. But if you directly go and implement it like we did in this class, how will you do it? Let's go ahead and try to implement it, okay? So AB, how will you do it? 2 NMOS in series. 2 NMOS in series. A, D. Oh, somehow. Let's try to. So A, B, like this. A, B. Then we have B, C in. Another 2 NMOS in series. B, C in. C in A. Another 2 NMOS in series, which is, isn't it easy? I don't know if you. So now we have implemented this. They are what? There is plus and so they are in parallel. We have implemented AD, BC, CA. C is carry in from the previous bit. Remember? So now we do the opposite for the what? PMOS. So AB in series, 2 NMOS in series. What we will do for the PMOS? 2 PMOS in parallel. Do 2 PMOS in parallel.
The speed is not the same.
Yeah. So our Boolean function is like this, right? Same B, same C in, same A. A, B, B, C, C, and that. So if you do exactly opposite here, okay. So what will be A, B? Now we have B, C. Now we have, sorry if my transistor looks small here. C, actually C means C, sorry, A. Now we have a pull up network. You see A, B, B, C, C, A, and they're in what? Series. A, B, B, C, C, A, they're in parallel. So there will be series.
You all stop to the
Sorry? Yes. I am trying to make the procedure simpler. That's why I'm telling you to disentangle pull up, pull down network. Then just do the opposite here. Doing opposite is easy, right? Okay, these two are in series. Draw two PMOS, they're parallel. These two MOS series parallel. Then do the opposite. So how many transistors do we have now? Okay, we have actually implemented this bar, right? We need another NOT gate here. So how many transistors are in here? Only 14 transistors. How many did we have when we tried to implement in this way? Sorry?
no.
We are not actually counting the transistor in here. We are counting the implementation. We have implemented it this way. We could have implemented it this way.
Yeah,
Yeah. How many? Oh, 14 is here. Yeah, 1, 2, 3, 4. Oh, not 14. I'm sorry. 1, 2, 3, 4, 5, 6. Oh, sorry. C, 6, 12, and 2. Inverter has 2. So, no. Each of them is 1. 1, 2. 1 PMOS, 1 NMOS, 1 PMOS, 1 NMOS. So we have 40 transistors here. So how many transistors do you know? Do we have here? Let me tell you. It has 6, it has 6, it has 6. And this is an OR gate, 3 input OR. I have not shown it this notice to you, but let me tell you. It has 3, 6, 8 transistors. So how many transistors do we have here? 26 transistors versus 14 transistors. It is for only 1 bit addition. For 1 bit, we are saving how many transistors? Huge, right? 12 transistors. So you are not adding 1 bit in your computer. You are adding millions and billions of bits probably. Okay? Calculating, not adding, multiplicating, dividing. So if you just if you follow this way, you will be needing much larger computer. But you should be able to implement it this way. Right? That's why we will try to implement a complex Boolean function direct, not by gate. We can do it by gate because let's say you are working on a breadboard, right? You have breadboard. So you bought these gates from market. You will have IC. You cannot break the IC and bring out the transistor and build this IC. Okay, then you can do it. But when you actually go to the real electronic fabrication, you need to have like this complex structure for optimizing area. Okay. So I will give you a very simple Boolean function to implement. Please try. Why? Because I have just shown you the error, right? One big error. So this is basically a very important part of the processor. Repeatedly, error, 1 bit addition actually does a lot of things. Okay. When you understand how two 1 bit adds with each other, you will understand how they multiply each other, how the subtraction happens, everything. Like you will automatically understand easy. So you don't have to worry about edit. I will just give you a Boolean function. Just try to implement it this way, okay, in transistor level. So I will try to implement this. So I hope you can see the Boolean function over this screen. That function, that is remain bad. So how many inputs are there? A, B, C, B, E, F, J. That's 8 inputs. If you can implement that, you can implement any Boolean function, right? Give it a try. Uh, at first implement the small chunks first. Okay, small part. You don't have to implement all of these. Very small part. Then try to connect it. And if you have the pull down reverb first, then go the pull. Because the pull up the pull up. So this is not an easy function to implement, right? That's okay, because once you understand it, it will be really easy for the smaller one. So anyone? Anyone? Yes.
Oh, it's
Yes.
well, this is it. Yeah, it belongs amplify one.
So anyone else? I will go ahead and try to. Yeah.
Say, I expect more things of even electronic figure on anyone else.
So I will go ahead and try to make this thing simple. So okay. So think about it. We have three different functions, right? One is a plus b, c plus d, and this whole thing. Can we divide the whole function is this small thing, three things? Okay. Try to implement this one first. So we have two NMOS in what? Parallel, right? Parallel. One is A, another one is B. Okay. Same goes for here, right? We have two NMOS. One is C, another one is D. Okay. So we are done implementing two. Now the last one. Last one looks a little bit difficult. Think about it. E, F, and GH. These three things are in what? Plus. There is a plus between them. What is G dot H? G dot H is two NMOS. G, yeah, two NMOS in series. GH. Then there is E and there is F. They are in parallel. E also is in parallel. One transistor only E, and another one will be what? F. So now this is one function, this is another one, this is another one. These three are in what? Dot, dot. So these three things will be in series. So connect these three in series. How does that will look like? I don't know how I can crop. Is there any option to crop? Let me think. Oh, no, I don't think I have the option to crop. So what you will have is something like this. So you connect here like with this and connect here with here and then a ground. Okay. Then you will have your pull down network. I'm sorry, I could not actually copy paste it somehow. Let's. Oh, it's gone for some reason. Okay, so you already got how we can implement the pull up network, right? So do the exact opposite, whatever you have done in your pull down network, and it will look something like this. Okay, it will look something like this. So I have already drawn this, right? This A, B, C, D, A plus B, C plus D, E plus F plus GH. You see, they are in series. So what we have here? A plus B, they are in parallel. We have A, B in series. C, D, they are in parallel. We have CD in series. E, F, and GH are in parallel. We have there in series. And these three functions are in series. These three are in parallel. You see, the larger ones parallel. Then we have pull down network, pull up network. Sorry. Are you guys with me so far? Then, as I told you before, connect an inverter or NOT gate because we implemented the complementary function. Anyone? So let me ask you now, go ahead and implement the function in gate. Can you do it? Just use gate, AND gate, OR gate, not gate, but I think AND gate or gate is enough. So if you divide it in gates, it will look something like this. So let me ask you, how many transistors do we have? We have actually 8 transistors here. 6, 6, 6, and 6. So how many? 32, right? We have 32 transistors. Now, how many transistors do we have here? 4 to 6, 6 to 8, 16, 18. So 32 versus 8. And just to give you an example of like, so please let me know if you have any question or if you think that you are not getting the idea yet. Or if you think that I can give you a little bit more overview about it. Because the next section you will do something yourself in the circuit lab, I think. Yeah. That's oh, that is excellent. Yeah. They are OR gate. I forgot. That basically OR. That's what you're trying to say? Yeah, yeah, yeah. But transistor count is same. Thank you. Thank you. No, 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 no. Thank you so much. Yes. P, yeah. E, A plus of. No, this is okay. This is okay. And the next part is also. I'm sorry. Please, if you take a note of this, you can connect it. So, what in our processor, we there is always calculations going on, right? One very important part of that calculation is that processor is ALU. ALU. So if you buy any computer, if you have your processor specification, if you elaborate the details, take the elaborate details of the processor, you will see something like this. Maybe 64 bit ALU or maybe 512 bit of ALU. So what is ALU? ALU means basically arithmetic logic unit. It adds, subtracts, divides binary digits. Okay. It does all the computation. Okay. So this ALU is basically built on these smaller gates section. Most of gates, there are other digital circuits and some of the complex Boolean functions that you've seen. Right? So it is really important if you ever build a career on digital electronics hardware or software as well, we have some rudimentary ideas like this in your future. So this is really necessary. And in our next discussions, in the next lectures, when you have, let's say, want to build a chip, okay, we will not actually design this large chip. We'll begin with basic few transistors chips, okay? But remember, in our processor, we have billions of trillions of these tiny transistors. So think about it, how we have to optimize the design, okay? Now, if you have a, let's say, any gate-based function or transistor-based function, how do we verify? If I say you already did it, give the design, your design is in your hand, okay? How do you typically verify? In simulation, at first you verify it by actually giving it ones and zeros in the input, and you observe what the output is, and you check it with the theoretical method. So, for example, you just fabricated a AND gate. If I give you an AND gate, how do you verify it? Anyone? You give 4 different inputs, right? At first you give 0, 0. You see if, okay, what is the output? 0. Then you change this bit and you see it's still 0. Then you change this. If you still see 0, is you get correct? No, it is not correct. So but you have to be cautious. You have to check for all inputs, right? At the beginning, if you see, okay, I have 1, 0. Okay, now it is 0. My gate is correct. My design is okay. Is it so? No, you have to check for all the inputs. So how many inputs do we have here? 2 inputs. How many combinations of input do we have here? What? 2 to the power 2, which is 4. If you have 3 input AND gate, you have 8 different combinations, 2 to the power 3. So you have to check for all combinations of input. How do you typically do that in a simulation or hardware as code? So let me actually go to the truth table, okay? Think about it. You have an AND gate. What is the truth table? So we have X, Y, and we have output. Okay. We have X, Y, and output. How many combinations of input do we have? 4. No, let's begin with 0, 0, then 0, 1, 1, 0, 1. And what will be the output? We all know. 0, 0, 0, 1. Now, I want you to concentrate on the lookup table. Look at the lookup table. You only have how many inputs? 2 inputs. Let's think about you have 16 inputs. Do you know how many rows you had? 2 to the power 16. I don't know what that is. You can do it in calculator. Would you draw the truth table like this? It will take you forever, right? So how will you verify your circuit? You will just drawing your truth table for the full day, right? You will not do it. So think about it. Look at this input. Look at this input, okay? We have 0, 0, 1, 1. 2, 0, 2, 1, right? Now, what do we have here? 1, 0, 1, 1, 0, 1. You are seeing a pattern. If I, are you guys understanding the question? Do you see any pattern in the input that I have written? So half of the row 0, half of the row 1. Now 0, 1, 0, 1. You see there is a pattern. If you have 3 input AND gate like this, if you have a truth table, let me show you how you can X, Y, Z, 3 input AND gate. We have 8 truth table, okay, right? 8 row in our truth table. 1, 2, 3, 4, 5, 6, 7, 8. Okay. If I tell you, okay, draw the truth table, you will think probably. You don't have to. What you will do? Let me tell you. Take the first input. Okay. How many row do we have? 8. Right? 4, 0. 4, 1. Now, go to the second one. Right? 2, 0, 2, 1, 2, 0, 2, 1. Then go to the third one. 0, 1, 0, 1, 0, 1. Your truth table is done. You see my point? Are you guys following? So, think about it. You now see a clear pattern, right? In your inputs. 0, 0, 0, 0, 1, 1, 1. 4, 0, 4, 1. No. 2, 0, 2, 1, 2, 0, 2, 1. Right? 0, 1, 0, 1, 0, 1, 0, 1. Right? So, if I give pulse here, so if I give pulse like this is our X, then this is our Y, This is our Z, let's say, and this is our output. Let's say. Now, can you see a pattern here? Do you see the period is getting divided by 2 each time? You see the period is getting half here. Each period is half of the previous one. Half of the previous one. Why have you done that? You see 4 0 then 4 1. The 2 0 2 1. You see the period is getting half of the pulse. So we have like 4 1 and 4 0. 2 1 2 0 2 1 2 0. 1 0 1 0 1 0 1 0. Now you will have all the combinations of input in you know pulses. You have 1 1 1 1 1 0 1 0 0 1 0. You see all the combination, all the possible combinations. And if you look at the output, you can verify all the combinations. Are you guys following? So for verification of any logic circuits or gates, you apply what? Pulse. And give multiplication of 2 in its periods in the input. For example, if you give a pulse of 500 hertz here, give a 1000 hertz here, give 2000 hertz here. You see? Then you can easily look at the level and you will know. Now, if my gate is working properly, I will get like this, an output like this. It is a 3-input AND gate. So we will have 1. Only where? 1, 1, 1. And for all the other cases, 0, 0. Right? Now we only have 1. Now you know, okay, my 3-input AND gate is working. Are you guys? So why have I discussed this? Because in simulation, you will build a CMOS circuit. You have PMOS and NMOS. Maybe an AND gate, maybe an AND gate, maybe a big Boolean functions that you give. How will you verify your Boolean functions? Like this. You give pulses in each of your input, but with different periods. And the period will be what? Multiplication of 2 of each other. That's it. So, for example, how we have simulated the sorry, mouse is on. Yeah, yeah. Thank you. Okay, for example, if we want to simulate a NAND gate in circuit lab, you will do it in the class right now. It is really easy. As you can see, 2 PMOS in parallel and 2 NMOS in series. How many inputs do we have? 2 input. And we will give the two frequency in the input. 2 pulse, maybe one is 500, one is 1000. Or maybe one is 1000 and another one is 2000. But it has to be multiplication of 2. Then you will look at the time graph. Okay, transient it is called. We'll do it in circuit lab and gradually follow it. And you will see how we can verify our gate is working. So what is that? When the NAND gate, what is the output of NAND gate looks like? Look at the truth table. It only gives you a 0 when both are 1. We'll look at the graph. It only gives you 0 when both are 1. So for doing that, I am just trying to show you how you simulate, how we typically simulate any function. So go to circuit lab. So please let me know if you can get it. So go to circuit lab. This is, I think you already have used, right? So have you simulated any transistors in this site here? So you already have, so go to file and new, okay? File, new. Now there is a window open and you can actually draw your circuit here. So scroll down and you will see somewhere there is MOSFETs and there is N channel and P channel MOSFET. So this basically means an NMOS and PMOS. Are you guys following the screen? Can you see the screen clearly? So you have two MOS. Okay, let's take the NMOS. So for the NAND gate, we have two NMOS in what? Series, right? Let's take two NMOS and connect them in this way. Let's connect two PMOS in parallel. Okay. Two PMOS in parallel. Now connect the wire. So take the wire at the very top of the component list. Wire and then draw it. Like click on anywhere and release the click on anywhere. Okay. Something like that. Now take the ground and connect the ground to the bottom of the here. And now take the DC voltage or VDD, connect like this. Are you guys, have you guys done this part, up to this part? Let me know. So we have two NMOS and two PMOS, two NMOS in series and two PMOS in parallel, right? And then do one thing. So this is, let's say, our A. This PMOS and this NMOS both are A. So what we do, we just connect them. Okay. And this is our B, let's say. You see, I am trying to, okay, one second. I am trying to connect these two. Oh, no, no, no. So, when two wires gets connected, there is a dot. Don't do it. Don't make sure that it doesn't get connected. So now we give a wire here, give another wire here. Okay. This is the two points where we'll actually connect our input. This is our output. Were you guys able to do this part up to? Okay, I'm giving you time, I think. So far, how many of you have got this far? Not yet. Any problem? Are you facing any problem while drawing it? Okay. I'm giving, I will give you a brief. It is really easy. So you can see the component list in the left side, right? You can scroll down and actually take a lot of components. You see there are a lot of gates, blocks. So these are the MOSFETs. Okay, take the NMOS, take two NMOS in series like this, and this is PMOS. Take two PMOS here. You can connect the wire by clicking on the wire in the top. You see, when you place the component, after that take the wire and click on anywhere and release the click on anywhere. So they will get connected, and then connect this. Now think about it. Like we have ground in the pull down network, right? And VDD in the pull up network. That's what I did. For that, we have a DC voltage here. DC voltage. DC voltage means 1 volt, 2 volt, 5 volt. So I have just taken it and connected it. And this is the ground connected. That's it. And by the way, I need to tell you, I have access to some advanced software here, but since you don't have that access, we are using it right now. But the problem is it will not let you do the simulation indefinitely. Suddenly it tell you to take membership. So if you hurry up, you don't have to do it again. Otherwise, okay, that's a good question. If you are, how many of you are done to this part? I think most of you are already done. So what I will go ahead and demonstrate it. You will see it in the video. So double click on the voltage source and okay, you see there is a value. Click type 5 on it. Why? These transistors are very old type of transistors which work on 5 volt. Okay. So nowadays transistors work on less than 0.5 something or 0.7 less than that. But it is a larger transistor, it takes 5 volt at least. So type 5 and enter. You see? So have we given our input yet? No. So for that we need this voltage function generator. You see, there is a voltage signal sources. The first one is voltage function generator. We will give pulses, right? I have already discussed. For verifying a gate, what do we need? Pulse. So I am giving this to here and another one connecting it to here. Okay. Then connect this, and connect all of these to the negative terminals to ground. Okay. Don't forget to do that. Connect all of the negative terminal of the voltage source to ground. Now, are you guys with me so far? Now, click on one of the voltage sources, okay? And you will see something like this. Now, in the amplitude section, in the right top corner, type 2.5. And the DC offset here, write 2.5. Why I will explain. Because 2.5, we are giving a pulse, right? So, we want 5 volt pulse. How much? 5 volt. So, that's why we need 2.5, 2.5. So, it will add up to 5, okay? And then here, instead of sign, take square. Type these things in your voltage source, voltage add. And then click enter. What? Yeah, same for both of them. No, not same for both of them. Remember what I told. Like Yeah, double the frequency will get changed or half. I have given 1000 here, entered, and now go here, do the same thing, 2.5, DC offset will be 2.5, and instead of sine I will have square, and instead of 1000 I will give 500. Now we have two frequency, right? 500 hertz and what? 1000 hertz, right? Enter. Now my circuit is ready for the simulation. I have 2. We are actually trying to build a pulse of 0505, right? 0 to 5 volt. So give 2.5 to DC offset and so it will be 5 volt. Okay. Now I will run a simulation. For running a simulation, you see there is a simulate. Sorry. That's the problem actually. So I'll go ahead and do it here. I think you can see. If we give simulate time domain, I am running a simulation from 0 to 1 millisecond. Okay. Don't worry. Probably. Okay. I have run the simulation, but I want to plot the input and the output here. And this is my input output graph actually. Oh, something is wrong with my circuit. Okay. 1 second. Oh. So that's the problem with it. So we are using a free simulation tool, which actually just give you maybe 15 to 10 minutes. Okay. For the circuit simulation. That's the problem. I have access to Cadence, HSpice and other stuffs, but problematically you don't have that, and you cannot practice it now. We are working on it. Probably you can practice it later, but try this. That's why I have just given you NAND gate. Okay. So I can use it though. How I can do that? I can just go to incognito window. Okay. Then I can draw the problem is I have to draw the whole circuit over again. Yeah. Still, it will not give you more than that much time, whatever be. So that's why I'm going to incognito again. I can launch the circuit again. I can build a new file. Okay. And I have to draw the whole circuit again because it's not saved. Okay. So if you run the simulation, my simulation was almost successful. The period has to be double actually. I did that. So when you run the simulation, the output will look like this. Okay. For the NAND gate. I have simulated it yesterday and just pasted this screenshot here. As you can see, the simulation will look like this. Like we have two pulses here, right? We have two different pulses. And as you can see, they have, I just taken each plot and pasted it here. Yeah. Oh, it will actually tell you to choose this a particular node. It will give you a pen. Then you click on it. Click on the input and click on the output. Then it will give you three plots like this. So I separated the plots for your convenience. Like this. Like we are giving these two are input. V2 and V4 are basically input. And we are giving two different pulses. 1, 0, 1 and 0. This is 1, 1, 0, 0. You see these two pulses have like twice the period of each other. Like second one has twice the period first one. Then actually we are able to verify all the four combinations of logical input like 0, 0, 1, 0, 0, 1 and 1, 1. And since this is a NAND gate, we just saw the truth table, right? When the NAND gate turns on, oh, Actually, I am wrong here. It is 0, right? It is 0. These three are 1. I'm sorry. These three are basically 1. Somehow I have written it extreme. So you see, we are getting 3 1 and only 1 0. When both of them are 1, we are getting 0. So can you try to simulate an inverter now? So for doing that, go to incognito window if necessary. Try it. Give it a try. So in an inverter, you just have one PMOS and one NMOS, right? You have only one pulse as input. One pulse, not two. Try to simulate an inverter if possible. So go to incognito tab, I guess. Then you will be able to draw the circuit again in circuit lab. Go to file new, like a file new here, and draw an inverter. Okay. So inverter looks like something like this. Then give a DC volt here. It looks something like this. So give 2.5, 2.5 is square at the input. And okay. Then just run simulation. Go to time domain. And this is 1 kilohertz. So you at least should take 1 millisecond, which is 0.001 second at the stop time and step. So this is my input and this is my, yeah, this should be my graph for the inverter. As you can see, if this is my input, this is my output. You see, for input 1, the output is 0, and for the input 0, the output is basically 1. See, if you can hide the signals like this or show. So I have shown the inverter last class as well. So I'm just trying to get yourself familiarized with the simulation tool, how we do the simulations, how we draw a circuit and stuff. Uh, so this is the circuit. I'm just showing you the circuit for in case you So were you guys able to do it? You did it? Yeah. So just using these parameters, run time domain simulation, it will ask you to select a node, select this wire and this wire. Then you see there are two voltages here, VU, these are the input and output. And then run again, you will see this graph, okay? And these are basically, one is your input and another one is your output. So if you run the, as I have shown you, if you run the NAND gate, it will be something like this, okay? So I am gonna wrap it up for today, okay? Uh, because I have some very urgent program to attend. So, but I want you to try this, and this is your homework. So try to implement what you should do is uh, implement these two Boolean functions in transistors and in gates. You see what I'm trying to say? Both in gate and transistors, and compare the number of transistors in both of these, okay? And this is your homework, give it a thought. And also, you have a lot of circuit simulation tools in online. Uh, one is Circuit Lab, you can go ahead and try it. But as I have said, you have to turn on incognito and redo the circuit again if you take too much time. So you can go ahead and try to two input NOR. Okay. This is not mandatory, the part one. But if you can, it's will really good. Simulate a two input NOR gate in Circuit Lab, or if you find any other tools, simulation tools that you have access to, that is fantastic. The third one is the mandatory, but first two you have to submit. Third one, you don't have to submit. If you can, you will have maybe extra grade or something. Okay, but yes, only this part has a bar, not all of it.
Both
Yes. Okay, I am making life simpler for you. That will be actually a little bit tough, I assume. Yeah, I think we are good for today. So see you next week, and hopefully next week we will actually discuss how, if we have our schematics or the design of the circuit ready, how we can begin actually doing the physical design, actual design. These are schematic. These are not actually how transistor looks like. You know, right? We have source, drain, we have gate, substrate, everything's right. How we design it. So this is called layout, physical layout. From the next session, we will discuss how to design physical layout, uh, and it will proceed to to the chip design, how we design chip, how we give our input in input output pairs, a lot of stuffs. So from next class, we will discuss that. Thank you. See you next week.